Hello, Chemistry 11. This is Mr. Chan. And today what I wanted to do was I wanted to go over section B in the assigned reading that I had given you last day. Now, in this case, again, we're taking a look at the periodic trends. So what I had asked you to do was read pages 317 to 324 and answer the following questions. So in your textbooks, if you were to take a look, on page 317, okay, it talks about atomic and ionic radii. Now, the one thing I wanted you to focus on, to be aware of, is when you take a look at this chart that you see on page 318, the circles on the upper left-hand side of each element box, this is talking about the atomic radius. Radius of the neutral atom. On the bottom right-hand corner of the box, right here, this is the ionic radius. So what happens to the size as it becomes an ion, whether it is a positive, or if you look on the next page, what you have is you have negative ions. Okay. Now, that's one thing I want you to be aware of the difference when you're reading through section B, because there's a difference in how question number 2 and question number 3 approach things. Now, I did ask you to fill the table in the back. Okay, so what you should see is your table should look something like this. Okay, so you should tell me what the trend is in the atomic radius, in the ionic radius, and in the ionization energy as you go from left to right and as you go down a chemical family. So if you did not get this done, what you can do is pause the video right now and take a look and take some time to sort of jot down these notes or to supplement your notes so that when you go through this, it just makes a little bit more sense. All right, hopefully you've had some time to jot this information down. And so what you should notice is this. As you go down, as you go from left to right across the table, the atomic radius gets smaller. As you go down a chemical family, it gets bigger. Now, the key thing I want you to understand is why these trends occur. Okay, don't just memorize it. Okay, and one thing I would like you to be aware of is as you are taking a look at this, take a look at the common term. In this case, it says more attraction. Okay, or less attraction. All right, so all these trends are based upon the attraction between the nucleus and the electrons. So you notice as you go from left to right across the periodic table, what you're doing is you're increasing the number of protons and electrons, and therefore you have more attraction. The idea would be like a stronger magnet. So the more and more powerful a magnet is, the greater there is in the attraction to whatever object. And so the magnet is able to draw the object closer to itself. As you go down a chemical family, what happens is because there's more shells, you have less attraction to the nucleus, and therefore the shells are actually further and further away. When you take a look at the ions, if you're going from an atom to a negative ion, take a look at what's happening. Why does it get larger? Is because notice there's a decrease in attraction. Okay? When you're going from an atom to a positive ion, notice there's an increase in attraction. Okay, so all of this has to do with attraction. So why does it become larger if it goes from an atom to a negative ion? Because there's a decrease in attraction between the nucleus and the electrons, and there's an increased amount of electron repulsion. But when you go from a neutral to a positive, you have an increased attraction, you have a decrease in electron repulsion. And for chart C, ionization energy, as you go from left to right, the ionization energy increases because there's again, increased attraction. As you go down the family, the ionization energy decreases is because there's a decrease in attraction. And there's also more repulsion. So take a look at these three charts and take a look at the commonalities between chart A, chart B, and chart C. If you notice a pattern, it's all about attraction. What is happening between the nucleus, the protons in the nucleus, and the electrons of the outermost shells? Now, one thing you should be aware of is this. Chart A, where we talk about atomic radius, and chart C are kind of related, okay? Now, let me give you an example here. So let's say the atomic radius. As you go from left to right, you have more protons, more electrons, there's more attraction. So let's say we take an example would be, let's say we have an individual here. Oopsie. So let me draw an individual. I'm not going to, okay. So let's say we have a person here. And let's say the person has a pet. So let's say we draw a bunny. Okay, so we have a little bunny. Okay, now what happens is this person and this bunny are in love. Okay, now you could think of it like this. The more attraction this person has to their pet bunny, what happens is they want to spend more time with the bunny gets closer to it. That is like the atomic radii. As you increase the number of protons and electrons, you actually have more attraction, brings it in closer. Now, notice as you go from left to right, the ionization energy increases. Okay, now what would ionization energy be? Let's say you have another person, okay? They want to take the bunny away. So they want to, they want to take the bunny away. Now, if they take the bunny away, you can think of it like this. If there's a stronger attraction between the bunny and its owner, this stranger, this other individual, has to work that much harder to take that particular animal away. This would be like ionization energy. So if there's a strong attraction between the bunny and its owner, the bunny is closer to the owner, and I'll put the word owner here. This would be like the nucleus. And so what happens is the bunny, which is the electron, is closer to the nucleus, and it takes more energy to take that bunny away. So the attraction is increased, so the radius is smaller and higher ionization energy. Now, you might say, well, Mr. Chan, how come as you go down a family, what do you mean by more shells, less attraction, you have increased repulsion of shells? So let's say instead of having only one bunny, let's say this owner has, let's have another bunny. So let's have two bunnies. Okay, now what happens is the owner now needs to sort of share the love between the first bunny and the second bunny. That's why there's a decrease in attraction because you have a second bunny that sort of pulls that attraction away. Now, what about this increased repulsion or shielding effect? These two bunnies might not get along. Okay? Now, so that is why what happens is when you go down a chemical family, what happens is there's more shells, there's less attraction, and there's more repulsion. It's just like having a second pet. Not only do the owner have to spread the love, there might be conflict between the pets. Now, as you go down the family, the shell gets bigger because, again, might be like having a third bunny. Let me draw this bunny in a different color. So what you have is a third bunny. Now, not only is there's less love to this third bunny, decrease in attraction, but now not only is there conflict between the red bunny and the blue bunny, but there's now also conflict between the red bunny and the purple bunny. So you have increased shielding effect or increased repulsion. This is why you have the atomic radius getting bigger. Now, why does the ionization energy decrease? Take a look. It says more shells, so more repulsion, there's less attraction. So let's say this person here in orange wants to take a bunny away. Now, instead of the purple bunny, if they say, oh, I'm going to take away the red bunny. Now, the red bunny will probably be easier to be taken away because it's further from the nucleus, less attraction, and as a result, very easy to remove. Okay, and that is why you have a decrease in the ionization energy, because the amount of effort to take the red bunny away compared to the purple bunny is a lot less. Okay, so take a look at this picture and see how does it match chart number 1 or chart A and chart C. Now, what about chart B? What about this ionic radius? Well, we could think of it like this. You could think of it like family dynamics. So let's say we have a parent here. And let's say this parent has 2 children, 1 and 2. Okay, in this case, again, this would be the nucleus. And these would represent the electrons. Now, let's say, for example, the nucleus is like the parent, and let's say the parent only has, let's say, $6. The $6, this represents the number of protons. So right now for a neutral atom, what you have is you have $3 going to one child, $3 going to another child. Now, let's say this particular parent decides to adopt another child. Okay, now what happens is now the $6 or the 6 protons, let me just erase this, needs to be dispersed between 3 children. Now each of them will get $2 a piece. Now, that's why you have less attraction. Okay, and why is there increase in electron repulsion? Well, it's like adding another member to the family. What you get is you get conflict between the siblings. And so what happens is the family needs to spread out. Less attraction, more repulsion. Now, you might say, well, what about if it is a positive ion? Why does it get smaller? Well, with a positive ion would be like, let's say, let's go back to our original. let's say we had the original two kids. Give me a second here. Okay. Now, let's say the original two kids, let's say one kid moved out. What happens is now that remaining child, in this case, the remaining electron, gets the full attention, all of the money from the parent, and they have free reign of the house. They don't have any conflict, and therefore, life is easier. That is the same idea here. Going from a neutral atom to a positive ion, you have an increase in attraction to the nucleus, okay? Just like going from two children to a single child, that one child gets all the allowance, and there's decrease in electron repulsion. There isn't as much stress or conflict in the house. All right. Now, the reason why I'm using these analogies is I want you to be able to understand the trends. I do not want you to just try to memorize these. Understand the attraction, understand, this analogy. How does it work? Okay. Now, when you go through your reading, a couple of things you should be aware of. Okay. As you proceed with your reading, and we go down here, a couple of things you should be aware of. One of this is table 11.8 on page 322. Now, you will notice it says IE1, IE2, IE3, IE4. What those mean is basically how much energy it takes to remove the first electron. That would be IE1. How much energy to remove the second electron would be IE2. How much energy it would take to remove the third electron? That would be IE3, and so on. Now, one thing I would like you to notice on this table, notice lithium, to remove the first electron, very low energy. But notice it jumps almost like 10 times to remove the second electron. Look at beryllium. Remove the first electron, fairly low. Second one, maybe double. But the third one, take a look. It is almost 10 times the energy. So the one thing I would like you to think about is why this pattern? Why this pattern? And the same thing you will notice, it seems to repeat itself. If we look at sodium, notice sodium, very low, then jumps to 10 times. Magnesium, it goes from a low to double to almost 5 or 6 times here. Okay? So what do you notice? Why this pattern? What's going on? And to give you a hint, it's related to the shells, the electron configurations of these elements. Okay. Now, the other thing I would like you to be aware of is when you take a look on page 323, what you have is a little pattern, a graph of ionization energy to atomic number. Now, notice helium, neon, argon in the same family. It's going down. Same thing with lithium, sodium, potassium. It's slightly decreasing as you go down a chemical family. It is exactly the same as what we had talked about here, about increasing and decreasing, but instead of using words, they just use it in graph form. Okay. Now, the last thing is this. You will notice on page, I believe it's page 324, you will see a summary of the trends for the periodic table. Okay. Now, I've talked about the atomic radius and the ionization energy. Okay. You might want to confirm that across the top, the ionization energy decreases. In some of your books, there's a mistake. But notice this thing in metallic properties. Metallic properties is the ability to give up electrons. So notice as you go from left to right, the metallic properties decrease, but when you go down a chemical family, the metallic properties increase. Okay, the question would be for you, why? Why do you think the metallic properties or the ability to give up electrons, so metallic properties is, let me write that down here, ability to give up electrons. Okay, why does it decrease as you go from left to right? Why does it increase as you go down a chemical family? Okay, and hint, 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 it has something to do with attraction. Okay, now you can think of it like this, if I'm going to help you with this hint. If the owner of a bunny really loves a bunny, will they want to give up the bunny? Okay, so if the attraction to a bunny is really large, or are they more willing or less willing to give up the bunny? Okay, so think about that. As you go from left to right, the attraction increases between the protons and the electrons. Is the element more willing or less willing to give up the electrons if there's more attraction? Again, if the owner really loves the bunny, are they more willing or less willing to give up the bunny? All right, folks, that was basically the lesson that you missed. That sort of summarized all of this material. I did give some homework in class. So when you come back to class, do check the homework board to see what is been assigned. All right, folks, thank you very much. Have a good day. Bye-bye.